Hi everyone. Next, we are moving on to the applications of exponential functions. In the applications of exponential functions, we normally deal with problems where a population is either increasing or decreasing in number. When a population is increasing in number, we call that an exponential growth, and when it is decreasing in number, we call it exponential decay. Exponential growth or decay doesn't matter. In all these application questions, we use the same formula. So all the relationships or all the populations can be modeled by this equation. A equals I times B to the power of T over P. So we'll talk about each and every letter and the meaning of them. So letter A stands for the final amount, or to be more precise, accumulated amount. Letter I stands for the initial amount. Now we're going to talk about the letters T and P that are on the exponent. Both T and P represent time. But letter P represents time period, and letter T represents time total. So the time period tells us how long it takes for one increase to occur, 1% increase to occur, so one period of increase to occur. So for example, we would be told, for example, that a population is increasing by 20%. How long it takes for the population to increase by 20%? That would be the period. If we're asked to find the population in a certain length of time, that would be the time total. We'll get into more details and explain it a little bit better when we look at the examples. Now we're going to talk about the last letter in the equation, B. Now B is what we call the factor. It can be the growth or a decay factor. I'm going to write for now just the word factor. It is represented by a decimal number normally. Sometimes it can be a whole number, right? Now, the values of B, bigger than 1, represent exponential growth. The values of B less than 1 and always bigger than 0, because B has to be a positive number, represent exponential decay. Now, the growth rate is different than the growth factor. The growth rate indicates by how much, and I will highlight the word by in here, by how much a population is increasing. And we say by how much it increases over a certain period of time, so the time P. Now, when it comes to decay rate, it means the same thing, by how much a population decreases, similar to that. Now, the growth factor is the multiplier that is indicated by letter B. Okay, so it is used this way. So you multiply by the initial population by a multiplier, or the letter B, to find out how much you're going to have in the next growth spurt. Okay, to determine the growth factor, we add a 1 to the growth rate. To determine the decay factor, we subtract the growth rate from 1. And we will materialize all these definitions in these two simple examples. So in the first example, a population increases by 28%. Then we're going to say that the growth rate is 28%. We like to write this in decimal form, so that's 0.28. The growth factor, on the other hand, is 1 plus 0.28. So that's 1.28. Just in case you're wondering, why do we have to add 0.28 to 1? When we think of growth factor, we think that the population was 100% of what it was, plus another 28%. So 100% plus 28% is 128%, and that's how we get 1.28. Similar to this, when we talk about a decrease in population, in this case by 40%, we'll say that decay rate is 40%, or 0.4. The decay factor will be 1 minus the decay rate, so 1 minus 0.4, so 0.6. It's a very common mistake people make, that whenever we're given a problem, like when we're given the rate, say 40%, they immediately substitute it for B. Now remember, growth rate is different than the growth factor. They're two different things, but they are connected. So half-life is the time it takes for a population to become half. To become half of the initial, right? Alrighty then. So let's move on to a couple of examples. I think that we know enough to be able to read the question and understand it. An island colony of seabirds increases by 75% every 2 years. Today it has 1,200 birds, and we have to find out how big the colony will be in 10 years and how big it was 6 months ago. So that's a general idea that we're talking about a population increase in here. And I'm going to read the question one more time, more carefully, so that I can identify what I'm given. So an island of colony of seabirds increases by 75%. So this number right here, an increase by 75%, will tell me one thing, that we have a exponential growth. And what we are given in here is the growth rate. So the growth rate of 75% will help me to find the growth factor, because that's what I want to actually use in my equation. So we're going to write 1 plus 0.75 equals 1.75, which is the growth factor. Now, the next part of the sentence says it increases by this percentage every 2 years. 2 years represents time. But which time are we talking about? Now, this is the key word we have to look for, every. So when we are told every a certain amount of time, we're given a period of time when this growth rate occurs. So we are given, in other words, the value of P. So we'll say P equals 2 years. Now, today the population is 1,200 birds, so this is very straightforward. So that must be the initial population. And we want to find out how big the colony will be in 10 years. So 10 years is the longer span. We can look at it that way, right? So that would be the total time. Okay, and we need to know the final number of birds, right? The number after so many years. So I like to write the information first, always. And now I'm going to start with writing the equation. So the teacher said that we have to use this formula here. So I'm going to write this down. And I will substitute everything I have and everything I don't have. I'll leave it as they were. So A is not known. I is 1,200. B is 1.75. T is 10. And P is 2. Now, one thing we need to remember is that we should always make sure that the unit measurements here are the same. And the reason why is because they communicate with each other here in the exponent. So we can't use different unit measurements. So use the calculator. So we have 1,200 1.75 to the power of 5, right? So you can tell actually, and we can talk a little bit about this. So 10 is the total time, 2 is the period when 1% increase occurs, right? So 5 times the population will increase by 75%. I hope that makes sense. So I'm gonna write the equation in my calculator. So 1200 we said times 1.75, and that to the power of 5. Oh, we're gonna get a big number here. Okay, so 19,695.7. I'll round down actually, because we're talking about the number of living things. So 19,695. That's how many birds will be present in 10 years, hopefully. Always hopefully. All right, so we're moving on to the next question. So the next question is asking, so it's the same idea, same problem, same information. So, but this time we're asked to find how big the colony was 6 months ago. So there is one thing that has changed in here, the total time. Okay, 6 months ago means that we are given that the time is 6 months. Remember how we said that we need to convert to same unit measurements? So we either convert 6 months into years or the 2 years in here into months. I'll convert 6 months into years. It's not too difficult. So I'll write in here 0.5 years. Now let's think about something else. Now we are going back in time here. So if we use this as the initial population of 1200, then we're going to use the time back as a negative time, okay? So guess what? We're going to give this number a minus sign. And we're going to use the exact same formula. So we're going to say that A equals 1200 1.75 now to the power of negative 0.5 divided by 2. All right, so negative 0.5 divided by 2, you can do that in your head or you can use your calculator. So divide 0.5 by 2, you get 0.25, right? So we go again, we're going to use the calculator here. 1200 times 1.75 to the power of negative 0.25, and we expect to have a number smaller than 1200, hopefully, yeah. So 1043, so that makes sense. So we're going to say 1043 seabirds were present 6 months ago from now, right? So these are the answers.